The average person doesn't think about the physics behind electromagnetism. This is usually because there is never any need to know of that sort of thing in every day-to-day life. But also, it's because there is a much more complex side to what we think about these fundamental keystones of the universe. In the 19th century, light was thought of as a wave. This was because all experiments used to find the properties of light concluded the same thing. Light was a wave. The most famous of these experiments being Thomas Young's double slit experiment. In this experiment, Young shone a light through two slits onto a screen behind it. If light was a stream of particles, then Young would have found two columns of light from the two slits. However, what Young found was that the light was causing an interference pattern on the screen behind it, with areas of constructive and destructive interference. This is the type of pattern we would only expect to see if light was a wave, and the two slits were acting as two different light sources in phase with each other. From this, there was only one conclusion: light was a wave. Fast forward to the early 20th century, physicists were investigating a phenomenon called the photoelectric effect. The experiment consisted of an electrical circuit with a galvanometer and a power supply, but also included an evacuated glass tube in which was a break in the circuit. A quartz window was used to let a beam of light in and hit a metal plate, as it was more transparent than glass. With this setup, we would not expect a current to flow in the photoelectric circuit, but when light hits the metal plate, electrons are ejected and travel to the other plate, causing a current. Current is the amount of electrons travelling through any given point at any time, and voltage is the amount of energy each electron in the current possesses. Kinetic energy is the energy required to keep a mass of mass m moving at a certain velocity v. To find the maximum kinetic energy of an ejected electron, we set up a current in the opposite direction to the ejected electrons, which makes the plate they are travelling to become negatively charged. This pushes the electrons back to the plate they were ejected from. But the more energy the ejected electron has, the more voltage is needed to stop the electrons. When the current is reduced to zero, then the electrons with the maximum kinetic energy have been stopped. Using the wave model of light, physicists predicted that increasing the amplitude of the light would cause the electrons to have a higher maximum kinetic energy when ejected from the metal. But when the intensity of the light was increased, the physicists saw no change in the maximum kinetic energy of the electrons. Increasing the intensity of the light only caused more electrons to be ejected from the metal. Physicists also found that the frequency of the light was affecting the maximum kinetic energy of the electron. The closer to the ultraviolet side of the spectrum, the greater the kinetic energy. The closer to the infrared side of the spectrum, the lower the kinetic energy of the ejected electrons. The experiment also showed that there was a cutoff point in the frequency where any light lower than the frequency would not cause electrons to be ejected. Even increasing the intensity of the light would not cause any electrons to be moved from the metal. The wave model of light alone could not explain the photoelectric effect. Then along came Einstein. Einstein used the earlier work of Max Planck and his theory that light consisted of distinct packets of energy. When using this model and treating light as a particle, the photoelectric effect became understandable. Increasing the intensity of the light would increase the amount of packets the light emitted, but not their energy. This explained why increasing the intensity of the light only caused more electrons to be ejected from the metal plate. By increasing the frequency of the light, it increased the amount of energy each packet of light possessed. The higher the frequency, the more kinetic energy each ejected electron had. When doing this experiment ourselves, we recorded these results. When we plot the frequency of light against the stopping voltage required to reduce the voltage of the circuit back to zero, we get this relationship here. However, using the equation E equals QV, we get a new graph which plots the frequency of light against the energy of the ejected electrons in the circuit. The coefficient in front of X is what is known as Planck's constant, 6.626 times 10 to the negative 34 meters squared kilograms per second. Our coefficient is 5 times 10 to the negative 34, which is slightly off because the filters we used to remove all frequencies were not perfect, so they let some other frequencies through. Another thing we can do with this equation is find the energy used to eject an electron from the metal plate. What we do is set X to equal 0 and find the y-intercept, which is 2 times 10 to the negative 19 joules of energy. From this we can create an equation to give us the maximum energy of an ejected electron. E equals hf minus phi, where phi is the energy used to eject an electron from the surface of the metal, the work function. But when the experiment was carried out, There was no delay between the light first hitting the plate and the first electrons being ejected. If the particle model of light was used, it showed that the first packet of light would have the same discrete amount of energy as all the others, so electrons would be ejected instantly. From these experiments, Einstein saw that there had to be a change in how we saw light. It was not a stream of classic particles because the light was able to create interference patterns with itself when put through two slits. But it couldn't be a classical wave because the photoelectric effect wouldn't work. So Einstein concluded that light acted as both a wave and a particle. A way to imagine this idea is with this picture here. There are two images in this picture, a vase and two faces. You can easily switch between the two, however you can't see both images at the same time. This packet of light is now known as a photon. Photons possess both wave-like and particle-like properties. It behaves like a wave when shone through two slits because the two slits act as sources and they interfere with each other. But it also acts like a particle when used in the photoelectric effect because the intensity of the light has no effect on the maximum kinetic energy of the ejected electron. Light being made of photons does raise some odd thoughts, such as, if photons have distinct energy states, how come we see light as a continuous distribution? This is because the change in energies between two photons is so small that it is not noticeable to us on this large scale. Another physics concept that has both wave and particle-like properties are electrons. Electron guns work by heating a cathode, giving the electrons high energy levels and ionizing them. They are then drawn towards an anode and are accelerated forward. The beam of electrons are then fired out and into a magnetic field and deflected due to their charge. This experiment shows how electrons act as particles because waves cannot be ionized. This is how electrons were described for decades as particles. However, further experiments were done. One of these was shooting a beam of electrons through two slits onto a screen, like the double slit experiment. The screen showed that the two beams created by the slits interfered with each other, creating areas of destructive and constructive interference. On these experiments, we can say that an electron beam cannot be a classic stream of particles, because if they were, the interference we see in the double slit experiment wouldn't happen. But an electron cannot be a classical wave, because waves cannot be ionized. From this, we can conclude that electrons have wave-like and particle-like properties. Our results from this lab show us that wave-particle duality can be used to describe electromagnetism and electrons. This is due to their ability to interfere with themselves, but also as they act as particles when observed in the photoelectric effect or in an electron beam. The answers to the questions in the lab will be at the bottom of the script.